Today's background is sort of fitting with the space theme of the demo in the first half of the lecture. It's a photograph of the night sky that I took while I was out in White Cliffs. And one of the nice things about going far west of the Great Dividing Range in New South Wales is that the light pollution drops right down and you can see just how remarkable the night sky is. My astronomy is not great, but I suspect Jono is not anywhere in this photo, and he's probably on the opposite side of the sky to where you're looking at as my background. But I'm sure either way, he's getting up to some adventures on his way back from the demo in the first half. So what I want to do in the second half is connect what we've been doing with the singlet state back to something we saw in lecture 6, which is the spin polarization principle, because it points out another interesting feature of entanglement. So you'll remember back in lecture 6, we had this idea of the spin polarization principle, which basically says that any state of a single spin is an eigenvector of some component of the spin. What we're really saying here is that if we take some arbitrary state for a single spin A, some superposition of up and down, it will be an eigenvector of an operator, which is the Pauli vector sigma times a direction vector n dot product for some given direction n. And the trick here is that you just have to find out which way n points to do it. Okay, what it basically means is that for any single spin state, there's some orientation of the measurement apparatus where we don't just get a +1 as an outcome, we're guaranteed a +1 as an outcome, right? 100% probability. What we didn't show in that lecture, and I left as an exercise to do separately, is that you can either show that the expectation value of that operator sigma dot n for some given n will be 1, or more significantly, that the sum of the square of the expectation values for the x, y, and z components will be equal to 1, okay? So what I want to show in this lecture is that entangled states violate the spin polarization principle. So we've got two states that we can consider here. One is the product state that has no entanglement. We saw that in the last lecture. I'm not going to show that that actually obeys the spin polarization principle here. I'm going to leave that proof as an exercise, mostly because I would use up probably the entire half hour and maybe even an hour doing all the algebra for that, simply because you've got to manage all of the prefactors alpha and beta for 4 different terms of up, down, and down, up, and up, up, and down, down. And keeping track of those and doing them in a way that doesn't end up with an error somewhere is a little tricky. Okay, if you should do that for yourself as an exercise. It's a good one to do, and my notes will be available on the course website for that, so you can check if you get it right, or if you get stuck, you can have a look. Okay. The product state obeying the spin polarization principle really just means that the product state is just, factorizable into Alice's state and Bob's state. And what it's really just saying is that Alice's state independently obeys the spin polarization principle. Bob's state independently obeys the spin polarization principle. And when I just multiply those together with no correlation built in, that corresponding state will also obey the spin polarization principle. In other words, what we're saying is the two systems do absolutely nothing but coexisting side by side, independent of one another in terms of physical outcomes. And all we're really doing is just building them into a combined space, which is sort of just a mathematical add-on, and really just you can disentangle them by factorization. Okay. The place where this gets interesting is when you look at what happens with an entangled state, and that's what I want to focus on in this half of the lecture. So what we're going to do is prove that the spin polarization principle fails for the singlet state. And in order to do that, I'm going to need a bunch of the spin operator relations that I had from the last lecture. So I've already got them up on the page. I'm going to do this solely for Alice looking at her half of the entangled spin. Bob doing it on his half will give you exactly the same result, and I'll let you prove that for yourself as an exercise, although it's kind of just copying something you already have. So what we have to do is walk through this step by step, right? Because you remember on the last page, the way we show this is if we don't have an arbitrary direction n, the easiest way to do it is to look at the expectation value of sigma x, sigma y, sigma z, take the squares, add them together, and check that they're equal to 1. So what we're going to want is the expectation values of the individual spins. So let's start with sigma z as our individual direction. This is now psi s sigma z psi s, as we saw earlier. This is one way to write a expectation value, and it's some of the reason why I wanted to do it in this lecture, so I actually, somewhere in the course, get a good example of doing expectation values well. So this thing would be psi s sigma z, and what we'll do is we'll expand out the ket side of psi s just so that we can work our way through what's going on here. Okay, so let's do that one first. This will now be 1 on root 2 up, down. So sorry, wrong shape bracket just there. Let me get that right. Up, down, minus down, up. Put the brackets in here, like so. Okay. As you know before, we can pull the 1 over root 2 out the front. So let's get that out the front, out of the way. We keep our chi-s here. And now what we're going to do is operate sigma z on the up, down, and the down, up states, right? And I'm going to skip straight to doing what the outcome for that would be. So we know that sigma z on up, down will be up, down. So this will give us an up, down just here. And then we've got sigma z acting on down, up. So this is minus sigma z on down, up is minus down, up. So we'll get down, up here. The minus will make that a plus, and then we can close that bracket there. Okay. Now the next step in this is that we're looking at inner products here, right? So what we can do is go 1 on root 2, and we can expand out the bra psi s. So this will now be 1 on root 2 up, down, minus down, up, like so. And then we've got the terms that are on the right. So this will be up, down, plus down, up. Okay, so the next step in here is just to basically work our way through and do the multiplication. So the 1 over root 2 times 1 over root 2 is a half. And then what we're going to end up with here is a bunch, well, actually 4 inner products. So we'll have up, down, up, down. So this is basically the first one times the first one. First one times the second one will be up, down, down, up. Then we're going to go minus down, up, up, down. And the last one will be the second one times the second one. So this will be minus down, up, down, up. Okay, and it gets a little tricky to fit this on the page in the end, but let's get that in there. All right, so what we need to do in here is basically clean up all the terms on our way through, okay? And what we can use in here is the relation that looks like A B dash, A dash B dash is equal to delta A dash, delta B dash. Okay, you remember we saw this yesterday. It's basically just the orthogonality relation for combined state inner products. So this thing will give us 1 over 2 here. Up, down has exactly the same labels on both sides. So it is the same state. So it will be 1 because what we're doing there is a normality relation, right? If you think about this in terms of A dash, B dash, A and A dash are both up, B and B dash are both down. So the two deltas there are 1. 1 times 1 is 1, okay? All right, if we think about this second state here, what we have is up and down. So A and A dash would be up and down. They're different. That's 0. The other two would do the same thing. 0 times 0 is 0. So this would be plus 0. The third one along, dude, is also going to be 0 because it's down, up, and up, down. So it's going to be minus 0. And then the last one on the end is down, up, down, up. A and A dash are down and down. B and B dash are up and up. So that's 1 and 1 is 1. So this would be minus 1 on the end here. And if we add this together, 1 minus 1 is 0. So this thing ends up being 0. Okay? Pretty easy to prove. We can now go through. I'm going to do it for X very quickly. And then I'm going to let you do it for Y just for a little bit of practice. And also just to I always like to hand students the Y versions because it's a good chance to practice their conjugates. Because if I do the Y versions and I let the students do all the X and Z versions, it's easy to get into bad habits of not doing your conjugates properly. And then when it counts, like in an exam, you don't know how to do your conjugates and it all comes undone. So I'm going to leave all the Y cases for the most part here for you to do to practice your conjugation. So let's just walk through sigma X here really quick. We'll do it a little quicker this time. Sigma S, psi S, sigma X, psi S. We would have 1 over root 2, psi S, sigma X, 1 over, we pulled the 1 over root 2 automatically out the front, so we don't need that there. And so it would be up, down, minus, down, up, okay? So just moving a little bit quicker than last time, I've already pulled the 1 over root 2 out the front. Here what we're going to have now is sigma X acting on up, down. So this will be 1 over root 2 psi S in the brass state times, so up, down will give us down, down. So this will now be down, down just here, minus, and then sigma X on down, up gives us up, 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 like so. And then, of course, we can expand the bra psi S back out again, right? So this will give us a half out the front, and we will have up, down, minus, down, up as psi S on that side. And then we'd be multiplying that by our new state here, down, down, minus, up, up, just there, okay? And then, of course, let me move my equals over because I'm going to need to. As we know from the earlier problem, this now breaks out into 4 inner products, right? So we've got up, down, 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 plus up, down, up, up. And of course, that's carrying a minus sign with it. So this here should be a minus. We've got minus, down, up, and down, down. And then our last state here will be minus and minus, so that'll give us a plus. Down, up, 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 like so. And then we need to put a bracket on the end. Okay, now we just work through these again in the same way, right? So this will be, let me just clean that up. Come on. So let's just do this. We've got a half out the front. Up, down, down, down is going to give us up and down don't match, so that's 0. Down and down match, so that's 1. 0 times 1 is 0, so that term will be 0. Minus up, down, up, up. Up and up match, so that's 1. Down and up don't match, that's 0. 1 times 0 is 0, so that one's 0 as well. Then minus dud, down and down match, so that's 1. Up and down don't match, so that's 0. 1 times 0 is 0, so that term's also 0. And then the last one we add on to it is down, up, up, up. So down and up, first 2 labels are different, so that's 0. Up and up, the second 2 labels are the same, that's 1. 0 times 1 is 0, so that's also 0. Okay? Add that up, we end up with a big fat 0 right at the end. Okay? And you can show this for yourself. Sigma y in here is also equal to 0. Okay? Good practice of conjugation. So what are we getting in here? What we find basically is that if we take the square of the expectation value of sigma x and add it to the square of the expectation value of sigma y and add it to the square of the expectation value of sigma z, we would get 0 squared plus 0 squared plus 0 squared is 0. Okay? And so what we're really saying here is that the entangled state violates the spin polarization principle. There's nothing intrinsically special about this. All it's really saying is that now we have a system where the orientation of one spin is no longer independent on its own in the sense that we can think about the spin being polarized, but it's influenced by the other one, right? And so that correlation in there has basically meant that if we consider one of the 2 entangled spins on its own, it no longer has its own independent spin that we can consider to be polarized in the same way as having a single spin. Something has changed about that spin relative to just an independent single spin. That's all it really tells us with this spin polarization principle being broken. There's something a little bit deeper underpinning that, though, because what we did was pull all these results together and basically show that the sum of the squares of the expectation values was zero. But if you think about what's underneath that, what we're saying is that the expectation value of sigma x is zero, the expectation value of sigma y is zero, and the expectation value of sigma z is also zero. And of course, if we did this for the tau state, so look at Bob's measurement on his particular spin, he would find exactly the same thing on his side. Okay, so again, this is good exercise. You can do this for you can do the spin polarization principle for Bob's side and show that he gets the same thing that Alice does in this particular case. So the spin polarization principle is broken for both of the spins once they get entangled together. What this is really telling us is something that we already know, right? What it means is that the experimental outcome of any measurement is equally likely to be plus or minus one. In other words, the outcome is completely uncertain, right? What we could do if we opened up our envelope in here would be have either a spin up or a spin down. And if we take the expectation value of those two cases of plus ups and plus ones and minus ones, they basically add up to zero. And it doesn't matter what direction we look at it in, because that correlation between those two spins in the entangled state, that correlation affects not just Z, but X and Y, as we saw at the very end of the first half of this lecture, okay? So this is often another place, once people have got past the whole, speed of light transmission, spooky weird, and then have done the whole, correlation is not just for Z, but also for X, spooky weird, they sort of resort to looking for another spooky weird. This is one of these things that some people really like to do with quantum mechanics. As soon as you defeat one myth, they put another myth in its place. A lot of people think, oh, there's something weird going on here because we know the state vector for the system, which means we should know absolutely everything about the system, which actually is the place where the assumption is not true. But in the middle of that, we know nothing at all about the outcome of any measurement of either component of the spin, right? So now we no longer have anything that tells us what the expectation value for the spin components is. It's almost as though when we entangle these two spins, the nature of them as a single spin has gone away because they're correlated together. The way I rationalize this is, again, coming back to this idea of the classical entanglement situation that we did in the last lecture, right? Actually, everything in here comes back to that framework, because once you see this whole entanglement problem through the framework of classical correlation, you realize there's nothing really special going on. What the exact state vector tells you is not what the absolute, every little detail of the system. It's not going to tell you what the spin direction is at any particular point until you make a measurement, right? But we already know that. We know that just for a single spin, right? That we can have a state vector, but we can never really know what the state vector is until we do a measurement. And when we do a measurement, then we go from there, right? But that state vector, before we do the measurement, is, for example, a superposition of up and down. And we know the exact state of the system from that state vector, but we don't know, right down to what the actual spin is until we do a measurement. The same thing happens here for the entangled state. The state is really just telling you information about the system within the constraints of probability before you do a measurement of the system, right? So it's reasonable that you won't know absolutely everything about the system. What's happening here is that the state vector is really just in the form you have for the singlet state, telling you that you have correlation in the system. And you don't know anything about the individual spins anymore once you build that correlation. But if you think back to the classical correlation experiment we did in the last lecture with the two coins, we have a penny and we have a Dogecoin. We arbitrarily mix them together so we don't know which one's which and put them into envelopes, right? We don't know anything about what's in either of those two envelopes, either if that preparation of the state's been done properly. All we know is we have two envelopes, there's two coins, one has to be in one, the other has to be in the other, and it could be either, we don't know, right? The thing we do know is that there's a correlation between the two. And so all we've really done in that system is given away our information of what the exact configuration of coin in envelope is in exchange for knowing that there's a correlation there. And of course, once we do that measurement, that correlation enables us to then, extract meaning out of the outcome of the measurements. In much the same way we would have this here. If we take a spin up and a spin down, and we might go, well, we know this one's up and this one's down, and spin polarization principles tells us, we can know about our individual spins. When we create our singlet state, what we're actually doing is giving up information about which of those spins is in the up or down, in exchange for knowing that those two things are correlated together. And then eventually when we do a measurement, we can use that information of the correlation to interpret the results, okay? So there's nothing really special or spooky about quantum mechanics in the sense that you can precisely specify the state vector for the combined system and lose information about the individual systems that make up that combined system. That's exactly what we give up when we do classical correlation as well, right? There's nothing strange going on here. All it is just the quantum mechanical equivalent of what we do and don't know when we do correlation in probabilistic measurement, okay? So I'm going to leave that angle of the singlet state there, and I just want to come back to one last thing before we finish for today, and that's to show you that the singlet state is just one of many maximally entangled states. I talked in the last lecture about how you get partial correlations, so a partially entangled state. There's a number of states that have maximum entanglement, and I want to point out 3 of them in addition to the singlet state, for no other reason than you'll go on in your physics courses and these will turn up. So we have our singlet state. You'll remember it yesterday. It's some mixture of up, down, and down, up. And I pointed out that there's a minus sign in the middle, and some of you would have gone, why shouldn't that be a plus? And I went, well, it can be a plus. There's another state that has that plus. So 3 of the other maximally entangled states are what we call the triplet states. The triplet states are T0, T minus, and T plus, and I'll explain where the 0, plus, and minus come from in a second. You'll notice that the triplet 0 state has the plus, okay? So it's some mixture of up, down, and down, up with a plus sign in the middle, right? The T minus and T plus, instead of being combinations of up, down, and down, up, they're combinations of up, up, and down, down, okay? And the sign connected to the triplet state, T plus and T minus, basically tells you whether it's a plus sign in the middle or a minus sign in the middle, okay? How these fit together, I'm going to leave calculating this for you as an exercise, because yet again, it's another really good exercise to do. If you take an operator that is basically the dot product of Alice's Pauli vector and Bob's Pauli vector. Pull these 2 things together, right? If if you take a dot product, this is really just sigma x tx plus sigma y ty plus sigma z tz. And you put the singlet state in there, or you put any of the 3 triplet states in. What you can do is work through that combination and show that whether it's the singlet state or the triplet states, they're all eigenvectors for the operator sigma t, okay? The result that you'll get, and again, you'll have my working for all of this on the website, so you can do it for yourself as an exercise and check it later whether you got the right result. The singlet state will give you an eigenvalue of -3 for the singlet state being the eigenvector. And the triplet states will all give you a corresponding eigenvalue of +1, okay? And as we saw back in lecture 5, it's perfectly okay in quantum mechanics to have equal eigenvalues as long as we make sure that we retain the eigenvector that corresponds to them as different states, okay? And so the one place where singlet and triplet states show up is if you take 2 hydrogen atoms and each of those hydrogen atoms is a proton with an electron whizzing around it, you can imagine that electron being its own sort of quantum spin system. Now what we do is we bring those 2 together and they form an entangled state. And they can form that entangled state in a number of ways. And those number of ways that we actually observe in that atom are the 4 states that you see here, the singlet state and the triplet state. what you find is that the singlet state has a lower energy than the three triplet states, which, because they have the same eigenvalue, are all at the same energy. And this is why they're called the triplet state. It's three states that all sit together. If you apply a field to that atom, what you can do is actually break the degeneracy. And so what will happen is that the T plus state will go up in energy, the T minus state will go down in energy, the T0 state will stay where it is. And you can see that those three degenerate states basically become a set of three on their own, which is where the name triplet comes from. Singlet state down, lower in energy. Okay. I don't want to go much further with those states. I'll let you play around with them a little bit. They're kind of fun, but I wanted to point them out right at the end of this discussion of entanglement so that when you get further along in your physics courses and you see them start to pop up, when you look at, Schrodinger's model of the atom and so forth, you kind of go, oh, I know what these are. These are what we dealt with as entangled states in second year quantum mechanics. So with that, I think I'm going to finish. I won't have any more on entangled spins in my half of the course, but when I do my optional lecture at the end on quantum computing, I'll come back to the idea of entanglement because it's kind of fundamental to that. And if you go on to other quantum mechanics courses, you'll start to see where entangled states become important. Where I want to shift topic in the next lecture is to start looking at taking our quantum mechanics just from spins to just sort of, a particle in space with an arbitrary position and momentum to connect back to some of the ideas that you saw in first year, in particular uncertainty principle, which will be the big focus of the fourth week of my part of the course. I'll see you next time.